All right, so let's do 2 more examples here of related rate problems. Okay. So we did one example in which we were trying to see how much the revenue was changing per day, depending how many units were being sold per day, and also at a specific value for that amount of units. Let's see, suppose for this next example. For this example, it tells us that the number of traffic accidents per year, so we're talking about time again, per year, per time, in a city of a population size P is equal to, let me write this one. Suppose this equation for the number of traffic accidents per year in a certain population is defined as, let's see, let's use A for accident. A equal 0.02, or let's do 0.002, 0.002 times P to the 3 halves, the 3 over 2. Okay, so number of accidents per year for the city of the size of population P. The number of accidents per year can be defined through this equation here. Okay, now let's assume, or let's suppose here, that the population of the city is growing at a rate of 500 people per year. Okay, so the population of the city is growing at a rate of 500 people per year. There we see the keyword rate. Let us find the rate of traffic accidents per year when the population is 40,000 at the city. Okay, so let's go through that 5-step process again. So again, first step, we want to identify the variables that are changing with respect to our time of interest. So what are the 2 variables that we're looking at here that are changing per time? The number of accidents per year, traffic accidents per year, and what else? What else are we trying to see is changing with each year? The population as well, population per year. All right, so those are our 2 variables here. The population per year, that's P per T, P per T, P per T. All right, and accidents per year. All right, call it A per T. Okay, so second step, identify an equation relating our 2 variables of interest that are changing with respect to our time of interest. All right, so do we have an equation relating population and accident? It's given to us right there directly. The number of accidents is defined in this equation in terms of the population. So there we have, once again, a given equation. So A is equal to 0.02 P to the 3 halves. Okay. So for this equation that we're given then the third step, let's differentiate both sides of this equation with respect to time, where time is representing year here. Okay, so for this given equation from step 2, what we're going to do next is take the derivative with respect to time of both sides of that equation. So d over dt of A equal to d over dt of 0.02. 0.02, and this is all together, so this is all attached by multiplication, so 0.02 P to the 3 halves. And I'll put parentheses though. So on the left-hand side, the derivative, well, first things first, for our differential, denote the variable that we're taking the derivative of, which in this case is a variable of A. So on the left side, we're going to have dA over dt, and the derivative of a is just 1. The derivative of a is just 1 here. Hold on, let me check my mic real quick. Test, test. Yeah, there we go. Derivative of 1 equal to, well, how do we find the derivative of this term? Power rule. Bring the power down, multiply by the coefficient, decrease our power by 1. So 3/2 at 0.02. Well, actually, first things first, define what we're taking a derivative of. So in this case, taking a derivative of a p variable with respect to t. So we're going to have dp over dt. Multiplied by 3/2 times 0.02. That gives us 0.003. That's a 0.003 here. Times p, 3/2 minus 1 gives us 1/2. Okay. So now that we have our implicit derivative here, actually, let me simplify this a bit more. Since on the left-hand side, we just have 1, then this is just going to be d over dt equal to dp over dt times 0.003 p to the 1/2. Okay, and for this implicit derivative that we have defined, let's identify the values that we're going to be plugging in and what we're trying to solve for. So let's look at this problem here. So it tells us the number of traffic accidents is given by this equation for in terms of the population. And then it tells in the second statement here, suppose the population is growing at a rate of 500 people per year. So the population is growing at a rate of 500 people per year. If this is representing the growth rate, the rate of change of how many people live in the city per year, then that 500 people per year is a value of dp over dt, the change in the population with respect to time. So the change in the population with respect to time here. So that 500 is our dp over dt. So dp over dt is 500. Okay, and what are we trying to find? We're trying to find the rate of the traffic accidents per year when the population is 40,000. Okay, the traffic accidents per year. Meaning we're trying to solve for the differential of dA over dt. So that's the differential, the rate of change, the relative rate, or the related rate that we're trying to find. Okay, so let me identify that here again for step 4. So step 4, our population is given directly to us as 40,000. And then we're told that dp over dt, the change in population with respect to time, is going to be 500. And again, here we're trying to solve for dA over dt. Okay, so now let's plug in what we know into our equation and solve for the unknown here. All right, so using our equation that we set up for step 3, we're trying to solve for dA over dt. So dA over dt is going to equal dp over dt, which is given to us as 500. So we're going to plug in 500 into this differential, multiply by 0.003 times p, where p was given to us as 40,000 here. So 40,000 to the 1/2. All right, so once again, we go to our calculators here, multiply all this out. So 500 times 0.003 times 40,000 to the 1/2, which is going to give us an exact value here of 300. Okay. So what does this tell me? This is telling me here, this 300, or let me be a bit more specific. So in this case, it's going to be the change in the number of accidents per year. It's going to be 300 accidents per year. Okay, again, to summarize what this is telling me, this is saying that if the population is growing at a rate of 500 people per year, then the number of accidents per year will be growing, or will be increasing by 300 accidents per year. Or I said by 300. The number of accidents per year will be increasing by 300 when the population is 40,000. All right. So if the number of people in the city is growing every year by 500 people, then when the population is 40,000, we're going to have 300 accidents per year, or the number of accidents will be growing by 300 per year. All right. Let's do one last problem here. One more for related rates. And for this problem, let's also speak about another business application here, known as a demand function. Right, the demand function. All right, the demand function represents, or is an equation that relates the price of an item and the quantity demand for that item. That's a demand function. You notice here, it's an equation that relates price, denoted as P, and demand quantity, which will denote as X, right, at that price point. Okay, so the demand function represents how much we will be able to sell, how much of a certain item we'll be able to sell, the demand for that item, for the demand of that item at a certain price P. Okay, so suppose for this example here, I didn't put example there. Suppose for this example, suppose we're given the demand equation, the demand quantity of an item is defined as follows. Suppose our demand function, our demand equation is defined as X equals the square root of 3025 minus P cubed. Again, this is the equation that's going to tell me how many units we might potentially sell at a certain price point. All right, so the amount of quantity, the amount of items that we can possibly sell that are demanded is equal to the square root of 3025 minus our price cubed. Okay. Now, suppose for this problem, let's do the two parts here. Suppose for part A. Suppose I find dP over dx. Let's find this related rate, the change in the price with respect to quantity, dP over dx, okay? So how are we gonna find this? We're gonna find this implicit derivative of this explicit function, dP over dx here. So let me write our equation again. Okay, so here we have x equal to square root of 3025 minus P cubed. Now, just like we have done before with implicit derivatives, we can start off by taking the differential of both sides of our equation with respect to our denominator. Meaning we could take d over dx on the left side, d over dx on the right-hand side. But let's see if we can write this equation to make that implicit derivative a bit easier to find, because right now we have a radical over an expression, over a polynomial here. Let's take the square root here and let's get rid of it. Let's get rid of it by squaring both sides of our equation. Okay, so by squaring both sides of our equation, that square root and the square will cancel out, leaving us with x squared equal to 3,025 minus p cubed. So now we don't have to worry about any radicals or applying any chain rule here, because now we just have 3 individual terms. All right, so always try to see if we can find any shortcuts. All right, so now we just have 3 individual terms that we're going to be finding the implicit derivative with respect to. Okay, so again, we want to find dp over dx. So like we have done before in the beginning of the section, let's first take the differential of both sides with respect to our denominator of interest here. So left-hand side, we're going to take the derivative with respect to x, and as well as the right-hand side, derivative with respect to x. Okay, so I'm going to skip a little step in between here. So derivative with respect to x. So we're taking a derivative of the same variables in the denominator. And once we take this derivative, the differential is going to go away. We're going to have dx over dx, which cancels out. So derivative of x squared with respect to itself on the left-hand side is just going to give us 2x. Okay. And now the derivative of a constant with respect to x, well, what's the derivative of a constant? Derivative of a constant is just 0 minus, what are we taking a derivative of here in the second term? P. So in this case, we're going to have minus dp over dx. We're taking derivative of price with respect to quantity. And what's going to be the derivative of p cubed? 3p squared. All right. So here we have, simplifying this a bit more, we have 2x equals negative 3p squared. I mean, move that to the front. Times dp over dx. And what are we trying to solve for? What are we trying to find? dp over dx. So now we need to get this by itself. We need to isolate that differential. And let's do that by dividing both sides by negative 3p squared. So negative 3p squared here. So this cancels out here. Oops. Leaving us where our implicit derivative of dp over dx is going to equal negative 2x over 3p squared. Okay, so here we have the derivative of price with respect to quantity, dp over dx. So this is how much the price will change as x is changing, as the quantity is changing. Okay. But now let's do part B here. Let's do a part B. And suppose for part B, suppose we want to evaluate dp over dx is the implicit derivative that we just found. Suppose we want to evaluate this derivative at p equals 10. Evaluate dp over dx at p equals 10. Okay. So here we want to take our equation of dp over dx. I'm going to set this equal to negative. Look at what we have here. We have 2 variables in this implicit derivative. We have x and we have p. But what do we know so far? All we know is what p is, which means that the denominator is going to be 3 times 10 squared. And on top, we're going to have 2 times, well, do we know what x is? No, it does not specify a value for x here. So does it mean we just stop and skip this problem? No. Can we find x if we know the price? Yes. Again, what are we given? This demand function where x equals the square root of 3,025 minus p cubed. So if we know the price that we want to set our item to, then we can figure out the demand quantity of that item. If we know p, we can solve for x. Okay, so let me do this on the side here. So here we're given that p equals 10. And if P equals 10, to find X, we use our demand equation by taking the square root of 3,025 minus this value of P here, cubed, minus P cubed. Okay, so plugging this in your calculator, so 3,000 times 10 is 100, times 10 is 1,000. So the square root of, so carrying this on the calculator, we get a square root, or we get a value of X to be 45. And that's the value that we plug in into X and the implicit derivative. So on top, we're going to take negative 2 times 45. All right. So we plug in what we know. And in this case, we had another variable that we had to solve for using an established equation. An equation that was relating our two variables here of X and P. Okay. To help us solve for this differential. Okay, so carrying this calculation, dP over dx at this price point and at this quantity is going to equal negative 0.30. So negative 0.30. Okay, so what is this telling me? This is telling me that the rate of change of the price, with respect to quantity, with respect to X, is negative 0.30. I don't think I specified money. Assume dollars, negative 0.30 cents. Okay. In other words, if we're increasing quantity, then the price is going to be decreasing by 30 cents, right? Don't forget, this is representing a slope value, a derivative, a rate of change. The rate of change in the numerator with respect to your denominator. This is telling me that if we increase our quantity, that will decrease our price by 30 cents. Okay, price will be decreasing by 30 cents for every increase in quantity at this price point. Right? At when, I should say this, let me include that part, when price is $10 and quantity is 45 units. Okay, so at this price point, at 10 bucks, the demand quantity will be 45 units. So at this price point and quantity demand, the price of our item will be decreasing by 30 cents. Okay. And that concludes this last section here of chapter 3.